Continuing on with class 24, here's an example. I believe we just did that one. Okay, it's this one. Wow, it's got a little out of focus. As a car engine block receives 2 kilowatts at its surface of 450 degrees Kelvin from the hot combustion gases at 1,500 Kelvin. During the cooling, near the cooling channel, the engine block transmits that 2 kilowatts out at its 400 degree Kelvin surface to the coolant flowing at 370 degrees Kelvin. Finally, in the radiator, the coolant at 350 degrees Kelvin delivers 2 kilowatts to the air that is at 25 degrees Celsius. Find the rate of entropy generation inside the engine block, inside the coolant, and in the radiator air combination. All right, so if you're not familiar with engines, we have a crankcase thing going on here. We got it looked like a Mickey Mouse thing. And we got like pistons coming down here and are attached to a crankshaft and different cranks, right? And here's a piston, but we got the explosion that's taking place there. And maybe, I don't know, I'm not doing a great job with my my diagram here, but we'll try to see. Now, so in a car engine, and especially in diesel engines, but I think most fairly large engines, there's cooling ports, especially water-cooled engine, that go all along inside the engine block, right? So that engine block might be actually much bigger than this. There's enough room for this thing to rotate and these parts to move right here, but there's also like little cooling passages. It might even be up a little bit high, like in this right there. Might go around and also into the intake manifold and the exhaust manifold. Those little passages have water, and I'll try to make maybe the outside of this look kind of bigger. They're probably not like right there, but we could make them all look right here and have them to the outside right here. Like these, they're a bunch of passages, and they do them in a bunch of different ways, but they're and like in diesel engines, they'll actually have like a liner, or some diesel engines, maybe even some gasoline engines, they'll have like a liner that fits in there, and that's where the cooling passage, the coolant will be on the outside of the liner. But anyway, and they'll even be in the head, right? There'll be some coolant in passages in the head, and that cooling water, right? It goes through a system, right? So there might be a pipe coming up through here. And it goes through a pump for sure, and then it goes into a radiator, right? And it doesn't really look like that right there, but there are passages in there, and there's little fins, and they don't really look like that either. But anyway, so air passes across this right here, and so it goes to the heat, right? So let's just simplify this and make them look like little boxes, right? And we won't talk about why the temperatures are different, but let's just go ahead and make them into different stages right here. So we have this stage right here, or this wall that we have as we're going through the thing. And we're going to have heat passing across this thing. It's the same heat everywhere, 2 kilowatts for this. But on this surface, we have this 1500 degree Kelvin happening right here, and we'll also make a little dash right here. So there's like a boundary that's going on here. It's passing in this gas, and then the surface is right there. That's what I'm drawing onto the thing, and it's passing onto here, onto this side right here, and that's the coolant, right? So there's the hot gas, and so this is a high temperature, but this thing, it's actually, there might be something right here that's passing it through, but we only care about what's this temperature as this thing is crossing the boundary, right? That's right there on the surface. So maybe I even want to make my boundary like right there. That's what I've decided the boundary is like right there. And so this is going to be the 400 degree Kelvin Is that true? Yeah, this is going to be our 450 degree Kelvin. It's taking place on this surface and over here. And then there's going to be coolant, which is going to go up at a high temperature. Surface to the coolant right here. And that's 370 degree coolant right there, which is going to go across. Now we're going to have like we're going to say that there's coolant taking place right here, and here's a chunk of the coolant. All right, so here's the coolant, and this is the wall, right? Cylinder wall, or you could just say maybe not the cylinder wall, but it's part of the block, right? So it's part. We call this the block, right? So yeah, that's good enough. And then here we're gonna have on this right here, because this needs to be a higher temperature than this. So here on the surface of this, they've said it's 350 degrees Kelvin. So here's the 350 degree Kelvin surface, and there's still that same Q dot going across this thing, right? In and out. This surface right here is this is the coolant. I'm sorry, one second. Yeah, so this is the. I'm sorry about that. Let me think. Let me think. This is the coolant at 370. And this is the other side, right? So this is the liquid itself into this thing. And it's 350 degrees Kelvin taking place right there. And then finally, it's going to pass through the radiator wall. The wall of the pipe that's like here. So I didn't draw like I could make it look like a pipe, but it doesn't really quite look like that. But this is the wall of this. The coolant is on the inside of this and coming out. And so right here, we're going to have that 350 degree Kelvin. And then on this side, touching it right there, it says to the air that is 25 degrees Celsius. So 25 degrees Celsius. Now I would have said actually that you need to have another temperature right there, but I think they already made the problem complicated enough, and this ends up being 298 degrees Kelvin. So anyway, as we're coming through here and we're taking a look at this, at each of these control volume 1, control volume 2, and control volume 3, we could apply, and once again, I forgot to draw my Q dot coming in. We could say, and of course, what we've decided to use is the equation, our main equation, the entropy equation, was that 0 equals dot Q in over temperature in minus Q dot out over temperature out plus S gen rate, right? So for control volume, and then of course it turns around so that then you end up with having S gen equals Q out over T out minus Q in over T in, right? So control volume 1, we go S gen control volume 1 is just going to be Q, which is 2,000, right? We go 2,000 watts divided by the in, the out. So we go, that's going to be over 400 minus 2,000 on the in, 450. So we've generated 0.5556 watts per degree Kelvin. Control volume 2, S gen, control volume 2, 2000 over, what do we say? It's going to be out over in. That's the 350, 370. Should play some music or something. Kind of boring without it. Watts per degree Kelvin. And then control volume 3. SGen. Control volume 3. And you get your 2000. Divided by, and we're going out, which is 298. Minus 2000. And that's 350. 0.9971. And I think this was in the 8th edition, but not in the 10th edition. I wonder if they decided that there was too much things that they left out, right? So okay, here's somewhere we're taking some accounting for where the generation of entropy occurs for these different heat exchanges. But there was some amount of difference between 400 and 370, so you kind of always need to account for what took place between here. And I would say that's sort of a boundary layer you could kind of think of. I mean, we need to go from a high temperature to a low temperature to get right here, but this is the coolant, right? So this is like the flowing coolant, and there might be some coolant at the boundary, because we understand when fluid is flowing, we have a no slip condition, and there's usually like this layer of small, well, there's just one little particle that's stagnant, but the rest of it, there's also like sort of a boundary layer that's kind of like sticky, sticking to the sides right there. And then the same, but then they didn't do that for right here between the 350 and the 350, right? You would think there'd be, but I guess they're saying like, you know, this might be the boundary layer for that. But what happened to the jump between there? I don't know. And then also right here, we don't mention anything about this. Now, I would think there'd be quite a bit of a boundary layer between what the surface temperature of this is and what the ambient air. This will not be the same temperature as the ambient air. There's got to be a temperature difference between the two. But I liked it, and so I picked it, and then I went like, it's got some flaws. Let's take a look at another example.